Hi, my name is Christian Mosch, Managing Director of the Industrial Digital Twin Association, IDTA. IDTA is the home organization of the Asset Administration Shell, or AAS in short, and the AAS is the standard for digital twins. I am very happy that we can share now some of the results of the joint working group between IDTA and the OPC Foundation. Within the IDTA, the question sometimes arises as how the two technologies, AAS and OPC UA, can complement with each other, because convergence of IT and OT is very important to the market. And the two technologies have to go hand in hand. In the joint working group OPC UA for Asset Administration Shell, many experts from both organizations have put their heads together and good concepts were developed, and we will see some of them now very soon. Many thanks go from my side to Christian Diedrich, who is head of this joint working group, and many thanks also from my side and the IDTA side, of course, to the OPC Foundation, which is also very open for IDTA, the joint working group, and the technology of the Asset Administration Shell. Only by working together we can develop many new innovations for the market and for the future. Thank you very much and have a good OPC day.
Hello, it's a pleasure for me to give you here a political, crystal clear statement from the OPC Foundation about the cooperation with the IDTA and OPC Foundation. Yes, there have been some hiccups in the past, but hey, that has been in the past. Looking forward, we agreed by meeting with delegations on the board of directors to find a solution how we can merge both technologies for the best of the industry. And this is why I can't agree more on Dr. Matthias Bölke's statement that we use the modeling of OPC UA and the semantic from the IDTA and we add the REST interfaces. And the technical people should describe this in much more detail. This is not exactly the level I can deliver. But here, the clear message to the market, we have a joint working group, they are very cooperative, working together, and that's exactly the best for all of us. With this, find more information.
Welcome to my short presentation. My name is Christian Diedrich. I'm the leader of the joint working group OPC UA for Asset Administration Shell. May I shortly introduce myself? I'm coming from Magdeburg and working at the Institute for Automation and Communication, IFAC. This is a freestanding applied research institute, and at the Otto von Guericke University, also in Magdeburg, and I'm dealing with automation since years. Okay, the starting point of our joint working group was that AAS become now standard, and there are relations to OPC UA, which has been standard over years. And this is a short picture here, which coming from the standard by itself, and we have put in some interfaces related to OPC UA. And this is I want to show you a little bit more in detail. From the conceptual point of view, the working group starts that we think that assets has an all-over life cycle. It's a long period of time from ideation, planning, of course, operation, and even after operation, we have something like recycling, or we use the same product once again in another plant. And there are a lot of information which should be represented digitally. And this digital representation has, of course, interfaces that the application can get this information about the asset. Relating to our scope, we have a look, of course, at AAS and OPC UA interfaces, but even there can be other interfaces, manufacturer specific, but it's not the topic of our topic here. Okay. More in detail, we have the AAS information model as well as the OPC UA information model. And you see it with the brown lines there. There are crossovers between them. So sometime one wants to have information about an asset with OPC, so one needs asset information over AAS using OPC UA information model, and vice versa with OPC UA clients wants to have information which are in the AAS internally. So to get this, it's principle technology independent, how you implement this. Important is how the interfaces are there. And so it's up to the vendor to decide which kind of implementation is done. To do it a little bit more abstract, we have applications which are purely on one side, but of course we have applications which want to have access to both interfaces. And now we start the individual parts which at least come to this crossover. So the first one is OPC UA AS transformation. If one wants to have information from the AAS and has an OPC interface, then we have to transform the AAS data from the AAS model into the OPC UA model. Sometimes maybe it's vice versa, then one even can have this mapping in the transformation in the other direction. The next point is if there's an application which has an AAS interface but wants to have direct access to the OPC UA server, then they need all this information. And for this, we have a submodel which is called OPC UA server datasheet. And this submodel provides the description of the features of the server, the endpoints of the server, even the node sets, OPC UA node sets are there. And sometimes also additional information about security is available. So the application may configure the client and get this information out of the AAS. It may be vice versa. There's an application of OPC UA. There's an OPC UA client, but needs information about the AAS and content. And we don't have to do anything in the joint working group because the asset ID is already part of the specification for OPC UA. And based on this asset ID, this registry and discovery, which is in the framework of asset administration shell, one can acquire the URL of the AAS, and so this application gets this information. The next point is, what about the online data out of the assets? One needs to have the endpoints inside the asset. And for this, there's a so-called asset interface description submodel. This is based on WebSync's description. And this described on one hand side the endpoint, but of course the address of the device by itself for an OPC UA server, the URL, yeah, and but can for Modbus, Profibus, MQTT or other communication means. So this is a universal description of interfaces to the asset by itself. If one wants to have this data from this asset variables and parameters inside the namespace of the submodels of the AAS, one needs a mapping between the data coming out of in the submodel, which is deferred to. Our example maybe here carbon footprint. The carbon footprint is related to the product, the power consumption is coming from the machine, and so one can map the data coming out of the machine into the carbon footprint one, which is dedicated to the product. Yeah, so one has this mapping also there. Additionally, this is more from the software point of view and maybe even from the scalability point of view. We want to have a common IT-based interface, WebSockets in our terms, and this is can be seen as some wrapper around both interfaces. So the interfaces by itself are as they are because they provide the model information, but the WebSocket is how the access can be organized. This is another topic we have, and last but not least, we have this overlap between submodel templates and companion specification over the years. Overlaps means that parameters, variables, which are one same in the asset, maybe are different described from different perspective of view in the OPC UA's companion specification or submodels in the AAS. And we want to identify these overlaps, and the intention is also to give maybe guidelines how applications can deal with this topic. Okay, I have tried to show you that we have really a crossover from the application point of view. The needed information can be provided for using different interfaces, and so the vendor can use technologies they are intended in, and their users, of course, want to have. So we have 4 working groups to do this. One is for the AAS OPC transformation. This becomes a companion specification. Then we want to have a specification for the WebSocket communication. And in one group, there's a submodel template for the OPC UA server datasheet, asset interface description, and the asset interface mapping configuration relating to OPC UA. This has tight connections because the endpoints and the description of the server datasheet has to be consistency. Yeah, and then at least we have our working group dealing with the overlaps. This was my short introduction. You get more detailed information about each of this topic, and thank you for listening. Bye-bye.
Hi everyone, my name is Sebastian Käbisch from Siemens. I'm leading the working group at the IDTA that covers 3 submodels. First, the asset interface description, then the asset interface mapping configuration, and the last one, the OPC UA server datasheet. In the next few minutes, I will give a brief insight into what these submodels are about. The Asset Interface Description submodel, or AID for short, enables the description of the communication interfaces of an asset or asset-related service. With this, you can express the details what kind of data and operations are provided by an, or for example, sensor actuator-based asset. And having this, you have the perfect baseline to enable plug-and-play asset onboarding. The AID also provides a facility for integrating runtime data into the AAS and can be utilized to fulfill the EU Data Act by providing the customer with an electronic description of how they can access specific consumer-relevant runtime data of the asset. The underlying technology and structure of the AID is based on the W3C Web of Things thing description. AID 1.0 was released last year, supporting 3 protocols, namely Modbus, MQTT, and HTTP. With AID 1.1, which is currently under review, we will also cover OPC UA, BACnet, and IO-Link. Below you can also see the members who were active in this working group. The next submodel which I like to present is the Asset Interface Mapping configuration. The Asset Interface Mapping configuration works together with AID and can be used to bring in or map a selection of data points offered by an asset interface. For example, if there is an OPC UA-based interface that offers a number of OA nodes that are described via the AID, the AIMC specifies which UA nodes are of interest and would like to have the corresponding runtime values mapped to an application-specific submodel. And the last submodel I would like to present is the OPC UA datasheet submodel, which can be used to completely describe an OPC UA server with all the details such as the namespaces used, possible security modes, information about array sizes, etc. This is useful, for example, when machine or robot builders would like to hand over electronic documentation on how the OPC UA server is configured. A customer can easily request these details, for example, via the AAS REST interface, and use this information to integrate the OPC UA server into its targets application. Here, I have also clarified the difference between the AID and the OPC UA datasheet. The AID has a more data method-centric view and provides only relevant information about this, while the OPC UA server datasheet provides the full information about how the OPC UA server is configured. Okay, I hope you have a good understanding of the 3 different submodules. If you still have any questions, please let me know. Thank you very much and bye.
Hello, my name is Tino Bischoff. I'm working as a research associate in the group Smart Factory Systems at Fraunhofer IOSB in Karlsruhe. I'm the chair of the sub-working group mapping of the AAS OPC UA joint working group. The goals of this sub-working group are to develop an OPC UA companion specification for a generic mapping of use case specific AAS data into an OPC UA information model. This will enable the hosting of AAS models in an OPC UA server. Additionally, this will make it possible to access information provided by AAS and OPC UA using OPC UA means. This will also support the creation of AASs and submodel templates using OPC UA modeling tools. There are a bunch of modeling tools available for OPC UA, and this will allow everyone to take advantage of the OPC UA modeling tool infrastructure to improve the creation of AASs and submodel templates. Additionally, the goal is to provide AAS submodel templates in the OPC UA Cloud library. The current status of our subgroup is that we have started working on the companion specification and we make good progress. We already have a general idea how to do the mapping, and now we're in the progress of writing this into the specification. Thank you for your attention.
Welcome to my short presentation. My name is Jakub and I am leading the subgroup Maintenance Similarities between OPC UA component specifications and IDTA submodels, which is a part of Joint Working Group OPC UA AAS. May I introduce myself? I am coming from Brno University of Technology, specifically from Group of Industrial Automation. I also work for Central European Institute of Technology, located also in Brno. Let's start with the problem statement. There are 2 sets of specifications, OPC UA component specification node sets and IDTA submodels. The node sets and submodels are formatted using XML or JSON files, or even PDF file format is used for their textual representation. These specifications describe the similar or the same parts of technical domains like electrical machinery and so on. They contain variables, classes, or another model-specific declarations using similar technical language, so there can be found some similarities. Elements of both sets can be compared directly using their semantic ID or any other reference ID, because many of them don't contain it. So the subgroup challenge is to identify the semantic equivalence among the descriptions rather than the exact textual match between variable names. We are trying to be aware of meaning of the context and also involve element descriptions which usually specify the variable in more details. The results then could be in form of semantic-based mapping or any other relationship-aware descriptions. Our solution rests in creating a script detecting the similarities that could automate this very time-consuming task. The path could also be accomplished from another side. So now our task is to annotate OPC UA component specifications for E-class references using their provided interface, and then compare these references with IDTA elements, which are usually almost referenced. Our action plan also contains the implementation of one of the natural language processing methods, which should detect similarities between the specifications directly from their textual representations. This should give us a confirmation or maybe reveal other similarities. That's about a quick overview of the subgroup tasks. Thanks for the listening.
Hi everyone, I will be presenting the status of a common communication sub-working group. A few words about myself. My name is Georg Biehler. I'm Senior Key Expert for Data and Semantic at Siemens. You might remember this slide from Christian's earlier presentation. As a reminder, two APIs are provided, one for accessing information as defined by the AAS API, for example, retrieving all submodels, and another as defined by OPC UA, for example, subscribe. The Common Communication Subworking Group focuses on how to access these APIs. It proposes to base it on a single set of established web technologies. By using a single set of technologies, both clients and servers can integrate more easily, reducing complexity and development time. In addition, we benefit from existing security protocols and practices, ensuring robust protection for data and communications. Base functionality defines a mandatory base layer built on REST web technology. API definitions are specified using OpenAPI, and proxy stub code can be generated with tools like Swagger. This base functionality is fully compatible with today's REST interface for the AAS. Enhanced functionality offers advantages for applications such as efficient data transmission, full duplex communication, and low latency. Providing enhanced functionality is optional and may be implemented only if use cases require it. Currently, we are discussing to use WebSockets for addressing use cases requiring enhanced functionality, such as, but not limited to, dynamic data. For operational, dynamic data typically refers to fast-changing data or data that must be transmitted quickly. For lifetime data, dynamic might mean that data changes infrequently, such as once per hour or even once in several months. For example, the firmware version. So, depending on the use case, the overhead of REST may necessitate a more efficient technology. A proof of concept developed by Siemens, ACAD University, IDTA and OPC Foundation will implement the concept discussed in the joint working group. The proof of concept demonstrates common communication for both in base and enhanced functionality, REST and WebSocket. It supports two APIs, AAS and OPC API, including the representation of information according to it. Generic mapping will convert AAS request responses from AAS to OPC UA and vice versa. The digital representation contains all information uniformly, whether originally structured as AAS submodels, OPC UA companion specification or vendor-specific models. Goal is presenting the proof of concept at the SBS fair this year. Thank you very much for your attention.